All right, in this video, we're going to do the FRQ questions. So this first one is non-calculator. We have this series up here. So it says S is equal to, and this is kind of new. We've got this series and we've got like a separate term here, a separate term here, and a separate term here. So the series S is like the combination of all three of those series. So it's kind of new, but let's break this down. First part says, part A of the FRQ says, just consider that series with this first part. Identify the type of series, determine if it converges or diverges, and if the series converges, find the exact sum. So the question itself kind of gives you a hint. Anytime it asks you to find the exact sum, that only works for geometric series. So, okay, I see that this is gonna be geometric. I'm gonna rewrite it. N is equal to 1 as 3 times 1 over 4 to the n, which now I can maybe see this a little bit better. It's 3 times 1 over 4 to the power of n. So I'm gonna call it a geometric series. It doesn't ask me to say why it's geometric, just it's geometric. If a series converges, find the exact sum. The geometric series converges because we know R is less than 1. It's 1/4, it's less than 1. And it converges to, or the exact sum is equal to the first term. So I'm just gonna say this whole thing is equal to the first term. The first term is I would plug in my first counter for n, I plug in 1. So this would be what? 3 times 1/4, so 3/4 over 1 minus the R number. This would be 3/4 over 3/4, which is just going to be equal to 1. So that's the exact value. I think it's all for part A. Okay, part B says use the integral test to determine whether the series converges or diverges. Clearly justify that the conditions for the integral test are satisfied. So on the actual AP exam, we know they rarely ask you to actually prove the conditions, but we're just going to state the conditions. And when stating the conditions, we're going to kind of think about it. So the conditions to use the integral test, I'm going to say let f of n equal to 1 over n natural log of n. Now, oh, there's a typo. This should say, oh, up here there's a typo, I'm sorry. Right here, this should say when for n is 2. So we have to start at 2. If n started at 1, this part right here would be 1 over 1 times the natural log of 1, which is 0. And I'd get 1 over 0, which is undefined. So that'd be a huge problem. So I should have fixed that. It should be a 2. So S is defined at 2. All right, so, and there's another typo here. It should just say n is equal to 0. That infinity should not be there. Just did a bad job catching that. Sorry about that. All right, so f of n is positive. It's continuous, and it's decreasing for n's greater than or equal to 2. We just kind of have to say that. And it's pretty obvious. So if I start plugging in 2 numbers for 2 and bigger, this is going to be positive. And it's going to be decreasing because the top is a fixed 1 and the bottom just keeps getting bigger. I don't need to do a derivative test or ratio, algebraic ratio to show that. I'm just going to say that it is decreasing, and I kind of just checked it. All right, so from here, I need to say the limit, or I'm going to find the integral from 2 to infinity of 1 over n natural log of n, dn. That will be equal to the limit as a approaches infinity, 2 to a 1 over n natural log of n. And then I have to try to figure out how to integrate this. So I'm thinking I'm going to say u is equal to the natural log of n. So du is equal to 1 over n. And then that works out because in the du there's the 1 over n. So this would be equal to the limit as a approaches infinity. I'm not going to write the limits of integration because I'm going to wind up changing. This is just 1 over u du. The antiderivative 1 over u du, this would be the limit as a approaches infinity. So it's the natural log of u, which is natural log of n, evaluated from 2 to a. So this would be equal to the limit as a approaches infinity, natural log of a, minus the natural log of 2. And I think we've done this problem a couple times by now. We realize that this limit right here is infinity, therefore the integral diverges, which means the series also diverges by the integral test. All right. All right, next part. Look at that last part of this the series. Determine whether the series converges or diverges. Justify your answer. Does the series converge? Absolutely. Justify your answer. So this idea, remember, behind converging absolutely, converging conditionally, only works for alternating series. For us, alternating series. They don't have to necessarily alternate, but for us, they always will. So I'm going to use the alternating series test. So the limit as n approaches infinity of the non-alternating part is equal to 0. I'm going to justify that. And 1 over n squared is non-increasing. I think that's pretty obvious. If I plug in values for n that get bigger, the bottom gets bigger, but the top stays the same. So overall, that number gets smaller, but it's non-increasing. Therefore, the alternating series converges by the alternating series test. So first part done, determine whether this series, so the alternating series, it converges by the alternating series test, and I justified showing that the limit of the sequence was 0 and that the sequence is non-increasing, and I stated that. So does the series converge? Absolutely. So to converge absolutely, we need to take away the alternating part, which is 1 over n to the power of 1/2. This series diverges because it's a p-series. It's a diverging p-series. I'm just going to say the words. Diverging p-series. Therefore, the alternating series converges conditionally. What that's saying is it needs the condition of the alternating component in order to converge, because without it, it diverges. So therefore, it converges conditionally. And there's my justification. I could say, no, it does not converge absolutely. That would also be fine. All right. Part D, determine whether this series converges absolutely, converges conditionally, or it diverges altogether. So let's just think about this for a second. This part of the series converges, this part of the series converges, but this part of the series diverges. So I cannot add up two converging series and a diverging series and have it converge. So this diverges. It doesn't say to give a reason. It just diverges basically because one part of it diverges. And that would be good enough for this one. All right, let's look at the next one. It's very similar. And the FRQs on the test will be similar to these. I didn't want to trick y'all too much this time. So this one, determining whether this series converges or diverges using the limit comparison test with this series. That's kind of nice. Okay, the limit comparison test says if I take the limit as n approaches infinity, a of n over b of n, and I get some positive finite number. So as long as I don't get 0 and I don't get infinity, then they act the same. So I need to specify, and I got to figure out, well, what does this series that I'm comparing with do? So I'm just going to start off by saying that this series is a converging p-series. And now I'll set up the limit And there's no zero terms in any of these. You should check that, but this is never zero, this is never zero for n greater than or equal to 1. So the limit as n goes to infinity of the original sequence divided by this one, or multiplied by its reciprocal, would be equal to, okay, I'm going to think the biggest term times the biggest term would be 3n to the 4th. So, and then the biggest term down here is just n to the 4th with a 1 in front. So since 3 is a positive finite number, our series act the same. So what I kind of think about that is, if one series divided by the other series, if it's always like basically, like if I divide one by the other and I get the same number at some point, it starts to hone in on just like 3, the ratio is, so this would be 3 times bigger than this one, then they act the same. If they don't act the same, then the like ratio between the two would be getting huge, like infinity, or getting super small. So as long as L is a positive finite number, therefore the series, our original series, converges by limit comparison, or the limit comparison test. I determine if this series converges or diverges. So this one, I'm going to look at the nth term test and realize that the limit as n approaches infinity, 5n cubed over 1, so the sequence, this is equal to 5 halves, which is not 0, therefore series diverges by the nth term test. All right. Determine whether the series converges or diverges. Let me come back to this for just a second. This last one. On the test, so if you get this one, I just want to say more about this one. Let's just pretend this converged, and this converged conditionally. Then overall the series would converge conditionally because it needs this alternating component. If they all converge absolutely, then it would converge absolutely. But if one of them diverges, they all diverge. If they all converge, but one converges conditionally, then it converges conditionally. And if they all converge absolutely, then it just converges absolutely. All right. Part C, determine whether this converges or diverges. So as soon as I see this, the nth term test is inconclusive because the limit of the sequence is 0. But as soon as I see exponentials, I usually think exponentials and factorial, I think ratio test. So the ratio test is the limit as n approaches infinity of the n plus 1 term divided by the nth term, or multiplied by the reciprocal of the nth term. This is equal to the limit as n approaches infinity, and make sure you state the limit. If you don't have limits, then it's not the same thing. The limit of, I'm going to keep it n plus 1 cubed times 2 to the n over, I'm going to say n cubed times 2 to the n times 2. Those cancel. This is equal to the limit as n approaches infinity. Okay, the top, the biggest degree term would be n cubed. The bottom is n cubed times 2. So this limit, I'm not going to rewrite it over again, I'm just going to say is equal to 1/2. And if the limit of the n plus 1 term over the nth term is less than 1, we know the series, I'm going to write it, converges. Converges by the ratio test. What this is saying is, not at first, but over time, it starts to act like this geometric series of it's just 1 over n. So that's a geometric series where the common ratio is 1/2, so all the terms, each term is found by taking a half of the previous term. So what the limit, or the ratio test, is looking at the limit of the next term over the one before it. If that's still approaching something less than 1, it basically acts geometric, so it converges if it's less than 1. if it's greater than 1, it acts like a geometric series where it would diverge. All right, determine whether this series converges absolutely, conditionally, or diverges. So this looks just like this one, right? That's that with an alternating component. So we just found that this, without the alternating component, that converges. Therefore, I don't even need the alternating part. Therefore, this series, the alternating series, converges absolutely. And I might write that the integral in the beginning, I could have written this. I think what I wrote already was fine. Converges, and we did that from part C, and you could reference that. Since that converges, it converges without the alternating component, therefore it converges absolutely. All right, again, so study hard. The FRQs on the test are going to be similar to these, so hopefully this helped. If you have any questions, ask me maybe next time I see you in class. Bye.